The next topic in our discussion of Einstein's equations is solutions of Einstein's equations. And the first subtopic is coordinate conditions and comparison with Maxwell equations. Now, why are we comparing Einstein's equations to Maxwell's equations? Well, they have some certain similarities. In Maxwell's equations, the vector potential A mu overdetermines the physics because there's a freedom to make a gauge transformation. We can replace A mu by A mu plus D mu alpha without changing the physics. And the similar situation arises in Einstein's general relativity, where the analog of gauge transformations are coordinate transformations. So there are certain similarities, but also certain differences between Einstein's equations and Maxwell's equations, and we can learn something by comparing the two. So the Einstein tensor, G mu nu, has 10 independent components. It's a 4x4 symmetric matrix, G mu nu. But the Einstein equations reduce the number of functionally independent equations to 6. Why is that? Well, the Yankee identities told us that this was identically true. So that reduces 10. 4 equations here make it 6. Leaving 4 degrees of freedom. In the 10 unknowns. G mu nu of x. So Einstein's equations tell us how to solve for G, but we mustn't expect to find a unique solution for G because there's this 4-parameter degree of freedom. Now, that should not come as a surprise. They correspond to the freedom to make coordinate transformations. X mu goes to x prime mu of x. Or equivalently written as a infinitesimal transformation on the metric tensor. We can change the metric tensor by this amount without changing the physics. So now we can draw an analogy with Maxwell. The vector potential A mu that appears in Maxwell's equations F mu nu, you remember, was d mu A mu minus d mu A mu. This is also not uniquely determined. It's only determined only up to gauge transformations. A mu goes to A mu plus the derivative of some scalar alpha. We change A mu by d mu alpha, F mu nu remains invariant. And so this is a symmetry of Maxwell's equations, just as Einstein's equations are invariant under a change of coordinates. And this is, as a consequence, you can regard this as a consequence of a Bianchi identity. It says d mu, d nu, f mu nu is identically equal to 0. So here the counting is, as opposed to 10 minus 4 equals 6, here we've got 4 minus 1 equals 3. So there's this 1 degree of freedom in defining the Maxwell field. Now, in practice, to solve Maxwell's equations, therefore, we do what's called choosing a gauge. That fixes the ambiguity. For example, what's sometimes called the Lorentz gauge is to write d mu a mu equals 0. Now you'll note by its very nature this is not a gauge invariant equation. Its purpose is precisely to fix the gauge and to fix the ambiguity associated with this degree of freedom. Another choice is so-called axial gauge. Which is just to set the naught component equal to 0. So we can do something similar for gravity. In solving Einstein's equations, we do the analog of fixing a gauge. But in Einstein's case, that means fixing a coordinate system. So if we borrow the language of Maxwell, we'd call it choosing a gauge, but what we really mean is choosing a coordinate system. As you may already know, this gauge principle is at the heart of the standard model of particle physics. The strong, weak, and electromagnetic forces are all described by generalizations of Maxwell's fields, Yang-Mills fields, that have this gauge invariance. And gravity is sort of like a gauge theory, but with some crucial differences. And this is one of these differences what a lot of people have spent trying to reconcile when unifying gravity and the other forces. For example, since we're on the topic, if you were to write Einstein's equations not in 4 dimensions but 5, then there would be, instead of having 4 vectors psi mu, there would be 5. And you can interpret the 5th one as the Maxwell gauge transformation and the mu5 component in the metric as the Maxwell potential. This is the idea behind the Kaluza and Klein extra-dimensional picture of the 1920s. So in that picture, the Maxwell potential is a component of the gravitational field, and Maxwell's gauge invariance is a consequence of coordinate invariance in the 5th dimension. So that was one nice attempt to unify the two. But we're in 4 dimensions still, and we have a freedom in choosing our coordinates, just as we had a freedom in choosing the gauge. Let me give you a few examples. There's something called harmonic coordinates. Which says that gamma lambda, which is defined to be G lambda nu, G mu nu, gamma lambda mu nu equals 0. And here's an exercise that the square root of minus g times g mu nu with upstairs indices, comma nu is equal to 0. This, yes?
How come the freedom to choose coordinates when we're using Einstein's equations manifests in just 4 degrees of freedom? What about rotations? That you said the 4 degrees of freedom correspond to translations only?
The general coordinate transformations are of the form x mu goes to x prime mu of x. Now, a special case of that would be Lorentz transformations, and they include the rotations. So there's no need to add anything to what we've already said.
I thought you said that the 4 degrees of freedom correspond to translations, or did I mishear?
No, I didn't say that. I said they correspond to general coordinate transformation. Yes?
So in a previous lecture, tutorial, we had some work on like degrees of freedom with respect to gauge transformation. So it's something like apparent number of degree of freedom minus 2 times the gauge degree of freedom. Is this related? It kind of looks like.
Unfortunately, I'm not aware of what you did in your tutorials, so I can't tell you whether it's related.
But anyone knows.
I think what he's saying is you lose 2 gauge degrees of freedom because, no, you have 1 gauge degree of freedom, so you lose 2 degrees of freedom.
Okay, good point. I'm talking about functionally dependent components. A separate issue is physical degrees of freedom. A photon has only 2 degrees of freedom, not 3. So this counting is not a counting of, and the graviton has only 2 degrees of freedom, not 6. So this counting is not a counting of degrees of freedom, but rather functionally independent components that we're going to solve for in our field equations. So it's a different counting that we're doing here. Any other questions? This choice of coordinates is convenient in quantum gravity because often in quantum gravity you want to preserve the Lorentz invariance. You want to fix your general coordinate invariance, but leave the rest of your calculations Lorentz invariant. And this has that virtue. Of course, you don't have to make it Lorentz invariant. It's just a matter of convenience. For example, the analog of the axial gauge might be G00 equal 1, G0 I equals 0, where I runs over 1, 2, 3. That has this virtue of fixing the coordinates in the same way, but it's not a Lorentz invariant condition. So that's the similarity between Einstein and Maxwell, but there are many differences. The most notable one is that photons don't interact with themselves. They're electrically neutral. So there are no nonlinear terms in Maxwell's equations that would indicate an interaction of A mu with itself, whereas gravity does interact with itself.
A mu couples to charged matter. G mu nu couples, well, it couples to everything. That's the thing about gravity. We go through the list of elementary particles. Some of them carry electric charge, some of them don't. So some interact with Maxwell and some don't. But every particle, whatever its internal quantum numbers, interacts with gravity. But what's equally important is because Einstein's equations are nonlinear equations, gravity couples to itself. And one way of saying that is it couples to energy momentum. But gravity itself carries energy and momentum, and so gravity couples to itself. So in this equation, in the case of Maxwell's equations are linear. In the case of Einstein, they're nonlinear. Now, this has a practical consequence that it's much harder to solve Einstein's equations than it is to solve Maxwell's equations. And there's no universal recipe for solving Einstein's equations. You won't find a book with the most general solution of Einstein's equations in it because we don't know what it is. The best we can do is to make educated guesses that simplify the equations and try and solve them. So you will find books that catalog all the solutions, but there's no systematic way of generating all the solutions. At least we haven't thought of one yet. We have to rely on educated guesswork. And simplifying assumptions. What would be an example of a simplifying assumption? Well, spherical symmetry is an obvious thing to try. And this is what Karl Schwarzschild did. Schwarzschild, Black Shield, I believe, German. In 1916, very shortly after Einstein wrote down the equations, so he didn't waste any time. Apparently he was on the front in the First World War at the time he was doing it as well. So let's look now at the famous Schwarzschild solution.
we're going to impose spherical symmetry and see how far we get and what spherical symmetry implies. And then we'll see how we can narrow it down to a form where we can solve the equations. Any questions before we move on? So this is subsection 2, spherical symmetry. And the Schwarzschild solution. So we start with df squared is g mu nu of x, dx mu, dx nu. There are 10 unknowns. Only 6 of which are functionally independent. Well, let's just note that flat space in spherical polars looks like this. dt squared is minus, sorry, ds squared is minus dt squared plus dr squared plus r squared d omega squared, where d omega squared means d theta squared plus sine squared theta d phi squared. So you might guess and in fact you can prove it, although I won't. I won't give you the proof that spherical symmetry says that the most general line element is a squared dt squared plus 2ab dr dt minus c squared plus c squared dr squared plus r squared d omega squared. You can show that that is the most general spherically symmetric line element. Where A, B, C, and R are functions of R and T. Intuitively, you think spherical symmetry means everything depends on R and T, apart from the d omega squared term. A, B, C, and R are functions of R and T. So we boiled it down to 4 unknowns. But we can do better because we also have the freedom of choosing coordinates. So let's go to coordinates . Let's go to coordinates x prime mu equal t prime, r prime, theta prime, phi prime. Where t prime is just t, r prime is capital R, theta prime is theta, and phi prime is phi. That's a possible coordinate transformation. So then we've eliminated one more Actually, I think the convention is just to call that d omega, not d omega squared. So now we boil it down to 3 unknowns. Let's go do it once again. Define x double prime mu to be t double prime, r double prime, theta double prime, phi double prime, where r double prime is as before, theta double prime is as before, phi double prime is as before. And e to the mu over 2 dt double prime is a prime dt prime plus b prime dr prime. That's another coordinate transformation. And now we get where e to the lambda is b prime squared plus c prime squared. And nu and lambda are functions of t and r. So we boiled it down to 2 unknowns, lambda and nu, which depend on t and r.
A couple of questions. One is in the second coordinate transformation. Why don't we have t double prime equaling t prime in analogy with the other variables and in analogy with the previous coordinate transformation?
Well, if we put t prime, double prime equal to t prime, we wouldn't have changed anything, would we?
And how does the previous coordinate transformation change anything?
It changes r prime into capital R.
And would you mind explaining again where the exponential comes from?
Well, we're free to choose. We're free to make any coordinate transformations we like. And how we parameterize them is a matter of convenience. I could call e to the new x and e to the lambda y. There's no need to write exponentials. We've chosen to write exponentials for future convenience, that's all.
So in the second line, should it be dr prime or simply dr?
Thank you.
And this drdt.
Yes. Thank you. So we boil things down to two unknowns depending on time and the radial coordinate r. So we can drop the double primes now. Just call them t theta r phi. So we've got ds squared equals e to the nu of r and t squared plus e to the lambda of r and t dr squared plus r squared d omega. Or, if you prefer, we've got a diagonal g mu nu in which the only non-vanishing components are minus e to the nu, e to the lambda, r squared, and r squared sine squared theta. So, two unknowns. Lambda of t and r, mu of t and r. So that was just kinematics, if you like. The dynamics is now obtained by plugging that into Einstein's equations and trying to solve the resulting partial differential equations. Now, to do that, we have to calculate the gammas that go with that metric, and then from the gammas, the Riemann tensor, and then from the Riemann tensor, the Ricci tensor and curvature scalar, and then from those, the Einstein tensor. So that's a straightforward exercise, but it's a bit long-winded, but you have to be careful to get it right. And what I'm going to ask you to do is to show that if we denote dots to mean derivative with respect to t and primes derivative with respect to r, then that component looks like that. that component looks like that. And I think when you do this exercise, you will understand why it was convenient to call them e to the lambda and e to the mu. Just it's a calculational device. I think that's all you need. Maybe there's another one. So those enable us now to calculate the Einstein tensor. So the first equation is the naught component, which I've chosen to write 1 up, 1 down. Is e to the minus lambda 1 over r squared minus lambda prime over r minus 1 over r squared equals 0. Now, why 0? What are we trying to do? Yeah?
Just to make sure, so if you write the dot, is that differentiation by r, and a prime differentiation, so like mu dot, is that differentiation by time?
Yes.
And then prime by r?
Dot is time, prime is space.
Okay.
What are we trying to do physically?
You're solving in a vacuum. There's no stress energy tensor. You're solving in a vacuum, so you're equating components. The Einstein tensor to 0.
Yes, that's what I was about to say now. Why am I putting it to 0? What Schwarzschild was interested in was the gravitational field produced by a spherical body of mass m. Now, the answer to that question will depend on whether you're outside the body or inside the body, if it were a star or a planet. And what we're interested in is outside, where there's no matter, there's no energy momentum. So we're going to put, the equation we're trying to solve is g mu nu equals 0. Now, if there's a star there, or a black hole, or something else, you might want to put a source term on the right-hand side to represent the matter distribution. But to get the Schwarzschild solution, we don't need to do that. So we're just going to solve the empty space Einstein's equations to begin with. and we'll worry about the T mu nu later on. So G naught naught equals 0. G11 equals e to the minus lambda 1 over r squared plus mu prime over r minus 1 over r squared equals 0. G22 equals G33 equals 1/2 e to the minus lambda mu double prime plus mu prime squared over 2 plus mu prime minus lambda prime over r minus mu prime lambda prime over 2 minus 1/2 e to the nu e to the minus nu lambda double dot plus lambda dot squared over 2 minus lambda dot mu dot over 2 equals 0. Actually, I'll call those 2. And I'll call this one 3. This is e to the minus lambda dot over r equals 0. Now, why have I not given a letter to that one, you might ask? It's a consequence of the Bianchi identity. So it's a true equation, but it's redundant. It tells us nothing new that we didn't already get from equations 1, 2, and 3. Yeah?
I'm still wondering about the equation of each of these components with 0. Are we equating this with 0 because G mu is proportional to the energy momentum tensor, and we're saying that components of that equals 0 because we're solving the equations in vacuum?
Yes.
Thanks. And I'm still a bit confused about if we are solving the equations in a space that contains a spherical mass. That I thought you said that we're yes. So outside the spherical mass, but if the mass is there, then shouldn't the energy? Why is the energy momentum tensor attributable to that and therefore non-zero?
Well, there's two answers to the question. One is for a physical object like a star or a planet, then there is a T mu nu when r is less than the radius of the planet. And in that case, if that's the physical situation we're interested in, we should put a T mu nu there. If we're only interested in the gravitational field outside the object, we needn't put the T mu nu. Now, a more interesting question is, let's suppose we had a black hole. Do we need to put a T mu nu at all? And the answer seems to be no, with one exception, the origin, r equals 0. Because according to our wisdom, when a star starts to collapse to become a black hole, it goes on collapsing and eventually gets crunched into a point of infinite density at the origin. We never see that because it's hidden by the event horizon of the black hole. So there's a lot of discussion about what really happens at the center of a black hole. Does the density really go infinite? Do we need to put a delta function singularity to explain what's going on at r equals 0? These are all questions which are still being debated, actually, which I don't want to get into today. So for today's purposes, we can just say we're looking at a spherical object, and we're looking at the gravitational field outside that object, where T mu nu is 0. And so we're solving the empty space Einstein's equation. Is that clear now? But the point I was making here is we don't need this equation because it's the consequence of the others. It's the consequence of the Bianchi identity. So we learn nothing new from that. So the equations we want to focus on are 1, 2, and 3. And 3 immediately tells us that lambda dot is equal to 0. And then 1 and 2 imply that lambda prime plus nu prime equals 0, and that lambda plus nu is some function of t. But we can always choose the time coordinate. Since lambda doesn't depend on t, it's just nu depends on t. See, lambda plus nu differ by at most. Lambda plus nu is a function of time, but we can always choose a t coordinate such that lambda plus nu is 0. This implies that lambda and nu are t independent. This is known as Birkhoff's theorem, actually. Spherical symmetry implies static. So we didn't put in the requirement that G mu nu be independent of time. We only put in the requirement that it be spherically symmetric. But we've learned that as a consequence of spherical symmetry, the metric is indeed independent of time. And then you can integrate 1 to find that e to the minus lambda is e to the nu equals 1 plus a over r. And the 1 is so and the a, for the same reason, is minus 2gm over c squared, which we usually abbreviate minus 2m. So to summarize, the Schwarzschild solution looks like that. And the constant 2m has a name. It's called the Schwarzschild radius. And at distances r going to infinity, the metric tends to the flat metric. And the significance of it, it describes the gravitational field outside the spherical body of mass m. Now, we've written this. To arrive at this result, we've chosen certain coordinates, and one can, which coordinates one writes the solution in is again a matter of convenience. Let me give you the solution in some other well-known coordinates. So-called isotropic coordinates. The harmonic coordinates that I introduced a few moments ago. And finally, Eddington coordinates. You notice this looks a bit like the Schwarzschild solution, except this part is different. And it's different in the following respect. There's a dr dt term. And that has the unusual, curious property that it's linear in the mass m. All the other ones I gave you are nonlinear functions of m over r. So there's a moral. You see, we look at the Schwarzschild solution, and you might think it's singular at r equals 2m. The GRR component blows up. Does that mean that there's something funny with the space-time? Well, not really, because we can go to other coordinate systems that are perfectly well behaved. So the moral is you should not be deceived into drawing conclusions that are true only in one coordinate system. We need to abstract coordinate-independent physics from all of this. And in particular, we can address the issue of singularities. See, some coordinates don't cover the whole space. That's another disadvantage. And mathematicians have something called complete analytic extensions, where coordinates do cover the whole space. And it's worth writing down the coordinate system introduced by Kruskal, which has that property. And this addresses the issue of whether we should have a T mu nu in the source or not. And we introduce two coordinates u and v that are related to the Schwarzschild coordinates r and t, like this. Shine t over 4m, cinch, whatever you want to call it. V is r over 2m minus 1 to the half exponential r over m cosh t over 4m. Then the metric looks like this, where f squared is 8m over r exponential minus r over 2m. Let me just make a comment. To get some feel for the Schwarzschild radius, the Sun, the Schwarzschild radius of the Sun is about 3 kilometers. So it's much smaller than the size of the Sun. And a proton is 10 to the minus 50 centimeters. But if a body is such that its radius is less than 2m, then we'll see in subsequent lectures that it's a black hole. However, the solution is not singular. At r equals 2m. But only at r equals 0. So the Schwarzschild solution does have a singularity, but its singularity, despite appearances, is not at the Schwarzschild radius. But there is a genuine singularity at the origin. And how can we tell? So this apparent singularity is sometimes called a coordinate singularity. It's not a real singularity. And so an obvious question is, how do we tell the difference between apparent singularities and real singularities? Well, if we compute a scalar, for example, the square of the Riemann tensor, this equals 48 m squared over r to the 6th. The virtue of a scalar is that this doesn't change with coordinates, and the r equals 0 singularity is therefore a genuine singularity. But you see at r equals 2m, everything's perfectly well behaved.
So what are the indices on the r? The indices on the r, is it mu dash or is it a v?
Mu, nu, rho, sigma, mu, nu, rho, sigma.
Okay.
Sorry.
Yeah.
So we ought to be able to describe the space-time of a black hole that's collapsed everywhere with the possible exception of r equals 0 in a smooth and respectable way. And this is what Kruskal coordinates are designed to do. They describe the space-time as I said, is what the mathematicians call the maximal analytic extension. So people doing black hole physics frequently find it most convenient to work in Kruskal coordinates. So that describes the simplest and first example of an exact solution of Einstein's equations, the one found by Schwarzschild in 1916. It's interesting that it was recognized then that something funny would happen for objects whose radius was less than the Schwarzschild radius, but no one took it seriously at the time, including Einstein. They thought that was some mathematical artifact. And it wasn't until, I guess, the 40s, or was it the 40s, I think, that Oppenheimer and Schneider reasoned that when a star is burnt up all its nuclear fuel, it will start to collapse and inevitably and inexorably go on to form a black hole. And even then, it wasn't taken all that seriously. People thought this was an interesting theoretical observation without any real substance to it. And it wasn't until the 1970s that observational evidence for black holes started to accumulate. And now they're commonplace. There's millions of them out there that we've seen and catalogued, and everyone accepts that black holes are the real deal. And they're described, if they're non-rotating, that is, by the Schwarzschild solution, the first solution that was found back in 1916. Now, there are certain generalizations of this. We can imagine a black hole that carries electric charge, and that will involve solving the coupled Einstein-Maxwell equations. We'll do that next time. And another generalization is to allow for the object to rotate. And we get another exact solution known as the Kerr solution, which describes most of the realistic black holes. Most of the black holes we observe out there are rotating, and they're described by the Kerr metric that we'll describe next time.
Are we going to go over the derivation of the Kerr solution?
The derivation of the Kerr solution, no, we'll quote the Kerr solution, but we won't go through the logic that Kerr went through to arrive at the solution. It's quite complicated, actually. Rather a clever solution. So we'll write down what the solution is, but we won't go through the agonies of how he found it. The Schwarzschild solution is also the source of the majority of the experimental tests of Einstein's theory. So it occupies a central part in everything we do. Good. See you tomorrow.